All right, cool. We got a yes. We got a couple of yeses. Good, good. All right, let's go ahead and get started with today then. I will hide meeting controls. We're recording. Yeah, all right, cool. Hello, everybody. How y'all doing? Hi. Midterm season yet? Anybody had a midterm already? Yeah, that shit sucks, huh? Yeah, it's okay. The season will pass and we will be triumphant, I promise. I see there's like half the people that are normally here, so something tells me there's probably midterms this week and maybe a little bit of next week. Good luck. Wish you the best. Study hard. That's what we do. Today's Wednesday. Yeah, we know what day it is. We're on week, what is this, week 6? So we're like almost halfway through the semester. Sheesh, kind of crazy. Kind of crazy. Means homework 4 is due today, and homework 5 is going to be dropped at the end, like sometime today as well. It'll be due next week. How was homework 4? Was it harder than previously? Yeah. It's kind of tricky, right? All the plotting and subplots and COVID data is working with real stuff, but it was kind of cool, right? There was like some pretty plots. Hopefully you saw some like interesting plots that looked kind of fun. I handpicked those. I spent like 2 hours trying to like find like the perfect plots to make that are a little tricky, but not too tricky. So I hope you enjoyed those. Anyway, and yeah, and then we're doing our best on grading. We realize we're not like super fast with it, but this is like the first semester we're trying to get them back in like a reasonable manner and not just like all at the end of the semester. So shout out to the interns. They're working hard. Most of you have gotten your first homework 1 and 2 graded, I think. But we're trying to pump through those as fast as we can. So stay, be patient with us. We'll do our best. We're doing our best. Jeff Goldblum approves too. Okay, so today's lesson. There's no like recap questions from last time. We're just gonna get straight into it. We did talk about plotting and working with real data. So now we've kind of established how to load data in with pandas, numpy.load text. So if somebody gives you like a CSV or an Excel spreadsheet, you should know how to pull it into Python and pull out the data that you want. Maybe you want a specific column of that data. Maybe you want to take the average of the column. Maybe you want to plot some information like COVID data that you did on your homework. But now we want to be like scientists, right? So like there's a difference between just like plotting raw data and like making a story out of that data. The whole point of like a figure in a paper or a plot is to tell a story. Like, what are you trying to convey to the reader? Is it just data, or is there a trend in the data? Like if there's an actual trend in the data, you want to tell that. You want to report that finding that you saw, so that people can make predictions based off those trends. That's a lot of what science is about, and data science. So the way we go about showing trends in data is by curve fitting. That's a very common way. So we can fit data, we can fit like dots or data points with like a specific model or a curve. In this case, a straight line accurately represents those points. You may have learned this back in like high school when you like had to draw your ruler and you learned y equals mx plus b. Oh, that was fun, wasn't it? It gets a lot more complicated than that. That's why we use computers to do it for us. So like once we like fit data, this allows us to tell like a general trend of the data, and it gives us statistical insights, like how well does our model fit the data, to what errors do we have on that. And this is like a really useful tool. So is there any questions about what I'm saying so far? Okay, if not, let's go ahead and get into it. So what do we need to do to start fitting? We call it fitting or curve fitting a model to data. You need data and you need a model. Pretty self-explanatory. Some function of X, it might actually be multiple parameter a function. It might be a function that depends on mass of a star, the radius of the star, how much iron's in the star, like all sorts of different parameters that you could just conjure up. Whatever model you can make with math, you can create it into Python. And then you have some data from the real world that you want to try to fit that model to and try to see how well it matches. In this case, I have some like sinusoidal data. So what might be a good model for f of x? Sine of x, good. Yeah, that's like a totally good, reasonable estimation. And then you can add different parameters to make that sine of x skinny, to make it fatter, to make it taller, to make it smaller, to shift it left and right. You can add all sorts of parameters to try to fit and see how that model specifically lines up with the data. So that's an example of what we need. That tells us what we need to have. And here's a real world example. Oh, sorry. Like the most basic case. So this data looks like a specific polynomial that you may have come across in your lifetime. I hope so. It's a cubic. And I want to try and fit that. Now we know the general form for a polynomial. It looks like maybe like a term a naught, just some coefficient, some number, plus a1 times x to the 1 power, plus a2, x to the second power, and so on, where you have like p coefficients, or p coefficients where you increase the power of the exponent of the x term to that power p. And you could sum over these and you create like a polynomial of whatever degree you want. P is the degree. So the highest value for p is the degree of the polynomial. So in this case, the degree of a cubic is 3, where you have 3 different coefficients, or 4 technically if you include the 0 one. But the way we curve fit in Python, like super easy when you just have a polynomial. Here's a really nice function. It's called np.polyfit. I'm basically just going to show you some really complicated functions. This is the easiest of them. You just give it some x data, give it some y data, and then you tell it what degree of a polynomial. So it already just automatically assumes that you're going to be using a polynomial. You can't use this on any other, like you can't use this on you can't use it on the sinusoidal data. That won't work. Well, maybe you could, but you'd have like 1,000 or million terms and it would be like some crazy oscillating thing. It'd be much better with a sine function. But in this case, if it is a polynomial like that one, then you want to use this function right away. Gives you the answers like that. And it'll give you a bunch of coefficients that best fit that data. So a0, a1, a2, it'll give you all those. It'll spit them out for you. Very easy. But we can do better than that. This doesn't really give you errors. How do I know how well it's fitting? I mean, sure, you could probably fiddle around with it and give it some arguments or something to do that. But we want a more general way of fitting any function we want to some raw data. And we want to be able to see how well it fits that data. So in order to do that, we need to kind of get more sophisticated. And we need to understand how curve fitting algorithms work in the first place. There's lots of different ones, but the best, or like this is kind of the golden standard, this is what you hope to be able to do. If your errors are reasonably distributed, like normal data, you're not dealing with any crazy data set, this is the way to do it. It's called minimizing chi-squared. Has anybody heard of what chi-squared is? Raise your hand. Yeah. If you've taken a lab class, you probably have 5BL, 5CL, maybe the 7 series labs. They like typically talk about chi-squared to some degree. It's how you fit a model to data. But I know when I first heard about it, chi-squared like didn't make any sense at all. I was like, what the hell is this? It's a cool X. It's different than that. Let me explain. It's like big equation or whatever, but all it's saying is you want to reduce the amount of residuals you have left over. So if I draw a line through the data, the residual is the distance between every point and that line, that model. So I don't have a picture right over it. This one on the future slides, I'm pretty sure. But if you have a line with some data points through it, maybe like I'll try to draw this really big for everybody. Fit some line and you have lots of data. Sorry for the folks on Zoom. It's just minimizing the distances between every point and that line. So you're trying to find a line that gives you the smallest sum of all the residuals. That's all it is. So that's what this numerator is. Y sub I just refers to the ith data point, just like in an array, right? You can iterate through all the different data points. So this might be data point 10, this might be 20, 30, 40, whatever. You index it in an array. And then at every one of those data points, you just subtract away the value of your model. So maybe you have a line that's like a little bit under it. That'll give you some value. And then you divide it by this sigma. The sigma is like the uncertainty. So this is like your error bar. How big is your error bar for that measurement? Most of the time, it's just some constant value, some systematic error bar. But maybe when you deal with like really complicated stuff, you might have different error bars for different value or for different points. That's what the I is there for. So in some cases, it's a constant error for all measurements you made, or some measurements might be different than others, and they might have different error bars on them. And that's why there's an I underneath. So you're just dividing the residual at every point divided by its uncertainty value, and then you square it and you add it all up. That's what chi-squared is. That's all it is. Add up all the residuals, how bad, or like the distance between your points in your model, and you divide it by the error bars. That's it. That's all it is. Now, there is a common issue that happens when you're trying to minimize this. And that issue is, okay, what if I have a model with like 1,000 parameters? I can like make some crazy sine function that has like so many parameters that it goes through every single data point. It literally touches everything. That's not a good model. Like that's like you're way overfitting. That's what we mean by overfitting. You should have many, 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 many more data points than you do model parameters. So back when we talked about the polynomial, if I have a third degree polynomial, I should have way more than 3 data points. Way, way, way more. Way, way, way more. At least maybe 100 or something. You should have many, many times more. The rules of specifically, it's like, but just as general practice, you should have a lot more data than you do have parameters of your model. Okay? That's just a common issue that may occur when you're first learning how to fit parameters to data. So just make sure that your model only has a couple parameters to tweak, or your data is like so big that you can afford those models or those parameters in your model, those coefficients, you could say. Is there any questions about this? Anybody have any idea what function might go well to fit this model right here, or this data? We can use as a model. Yeah, x squared could be a good one. E to the x, yeah, both of those could be good. And the way you would tell which one fits better is which one has a smaller chi-squared value when you optimize it. So you try to fit different parameters, or like the e to the x and the quadratic. You fit them with all their models, and then you see what their minimum chi-squared values are, and you determine which one is better by which minimum chi-squared value is smaller than the other, basically. That's how you would tell. That's oftentimes what scientists do. There's a lot more steps involved. I'll let the lab classes teach you about the statistics. I'm just here to show you how to code it. But just had to preface that so we know what's going on under the hood. Okay, so now we're prepared to get into more complicated functions. So scipy.optimize has this, or scipy library. It's like NumPy, same kind of idea. But scipy is also like a huge library dedicated specifically to scientific tools. They have a really cool optimize sub-library inside with a function called curvefit. This is the one we're going to be using. So you'll notice it's a little different than the other import statements. Normally we did like import library as name, where that name was an alias. This is a little different. Python allows you to import direct functions from a whole suite of code. So maybe you don't want to load in the millions of functions that scipy has at its disposal. I literally only want one of them. So why should I add so many variable names where like you have every function name possible when I could literally just only take one? That's the only one I need. So that's all I'm saying. We're doing from this library, import the function I want. That's it. Okay. I'm just restating that. This way you only take the curvefit function from the library without typing anything else. And yeah, you don't pollute your namespace, which is more important. You don't want, like maybe there's a function in scipy's library called min, and that overwrites the minimum function of like the math library or the NumPy library that you're using. You don't want to like have conflicting names. So you just import that one function just for sake of use. You could import it a different way, but this is the way we like to do it. And now let's get into how it works. So this is a curvefit function. So it takes in some arguments and it spits some stuff out. So curvefit takes in a model. This is any function that you want to write. We'll show you exactly how you write that model function in a little bit, but it's some model. Maybe that's a sine, maybe that's a polynomial if you wanted to. It's kind of redundant, but you could. Maybe it's some crazy Fourier series where you have hundreds of sines and cosines. It could have exponentials, logarithms, whatever you want. Then you have an X data and Y data. So this is like an array of data values for your X and Y. They have to be the same size, same shape. So you can't have like 1,000 X coordinates and only like 100 Y points. That wouldn't make any sense. You have to have 1,000 X coordinates for every 1,000 Y coordinates. And then these are like the really important things that people tend to mess up and are most confusing. So let me explain them. P naught is a parameter that gives you initial, or that you're supposed to put in, and it's the initial guesses you're making to help the function out. So if you don't give it initial guesses, it has no idea what number to start at. So these aren't super important in the sense that you don't have to guess right on the nose of like what you think the parameters would be, but they have to be in the right ballpark. So for example, with this function, I shouldn't be guessing if it's maybe let's just pick a quadratic. I shouldn't be guessing negative values for the quadratic, right? Because it's going positive. That would confuse the shit out of SciPy curve fit. Don't do that. If it looks positive, like at least make it some reasonable value that's positive, not negative. Things like that. Just like don't make it a trillion for the amplitude of your quadratic. It clearly only goes to like 4 here. You don't need to make it like 20 or 1,000 or 10,000 x squared or whatever. It's not going to be like that. It's going to be like some reasonable number, maybe like 10, maybe 1. You could be off by quite a bit. I could even say it's probably 100 and it would be fine, but they're just reasonable guesses of what you think those coefficients are. And by coefficients, I mean like the little parameters that you can tweak to like make a sine function skinnier or thicker or taller or shorter, whatever you want. These are like little coefficients, we call them. Okay, so that's the initial guess. It's like an array, and it's like however many parameters your function has, it's like in that order. So I'll show you like how they correspond in just a second. Then the next parameter is sigma. This is literally, quite genuinely, these sigmas right here. It's an array of values, of like uncertainty values for every data point. So if you have an error bar for every data point, it's those error bars. If you don't have error bars for every data point, you should probably think about why you're curve fitting. Are you fitting like because you don't have error bars? That you probably should, but you don't have to. It can still fit a function without them. But scientifically, like if you're in a lab, you should probably have error bars. Or it could just be a constant value. You could set it equal to 1 or something and just say every data point has the same error bar to it. Cool. So that's what sigma is. It's just your error bars. And then bounds, this is an optional parameter, which goes like kind of hand in hand with the P naught. And it just tells you, okay, what range of values do I want to explore my P naught? So of my parameters. So maybe you say like, okay, it's good to look from values 1 to 10, but don't go to 10 million. Don't do that. Or you're telling it, don't go negative. That's like what the bounds mean. And yeah, so let me move my thing so you can see what the model looks like. So let me show you how a model function looks like when you code it. So any model function, you can give it any name you want. It doesn't have to be the word model. I just wrote model because it's model going into the function, but you just give it the name of the function you write, following that same functional syntax. Def for define, model is the name, and then inside the parentheses is the arguments. Now notice how the X is highlighted orange. That means that whatever the first parameter is in your function, it's going to be like the continuous variable. So that is not a coefficient. A1, 2, and 3 are coefficients. Those are going to be what the curve fit function is like tweaking and trying to find which ones best fit that model. So the X is like your continuous variable, and you just return whatever value. So in this case, we're doing a function A1 times sine of X to the a squared power plus 3. So now my model function is going to play around with A1 to A3 and see which one best fits my data. Okay. So it starts fitting parameters from the second argument onward. So I glanced over it at the very top, but you can see that I set fit params equal to curve fit. All I'm doing is saying that the curve fit function spits out values, and I'm assigning it to fit params. Now, fit parameters is going to be a list of things. The 0th index is going to be the actual values you want. The first index is going to be how you're going to get errors. It explains it in your homework. I'm not going to go through it in lecture because we don't really have time. If you've ever heard of a covariance matrix, it does stuff like that. But the first index allows you to get errors out. The 0th index tells you what the values are. Okay. So fit params 0 should give me what A1, A2, and A3 are in a list. It'll give me an array of values. And then if I change the index to 1, it'll give me a complicated data structure that actually allows you to find what the errors are on A1 and A2 and A3. So how badly or how much certainty does the algorithm have on that those are the right values to fit your data to? And that'll be on your homework this next week, and you'll be able to read about it. It has like a lot of exposition on the topic. Is there any questions? Okay. If not, then I think Raphael's going to take over for a little bit on the next subtopic.
Yeah. So for everyone who I haven't lectured yet. So I'm Raphael. I'm one of the instructors. So I'll be talking about root finding. So it's sort of similar to curve fitting in the sense that it's something that's almost quasi impossible to do by basic math, but the computer lets us do it really easily. So yeah, basically it's sort of blocked in the upper corner here. But you have equations like this, right? Like root 1 minus x squared equals sine x. You can't solve that by hand. It's impossible, basically. And even if you use some type of online calculator, actually, it would still be difficult. So this is where SciPy again comes in. So using this SciPy.optimize, we can use the root function, which essentially just solves for the roots of this equation, essentially the x's that fulfill, for example, the equation defined like this. So as you can see in our code, we define the function square root of 1 minus x squared minus sine x. Of course, you always want to make it so that the function is defined as one side, and then it's going to find the roots that let that equal 0. So you're going to subtract the sine x from the square root part. So then you can define some solution is equal to root of func and x naught. Your initial guess, as in the previous case, can often be important. You should guess by plotting and looking around. Obviously, you could also find the solution by plotting and looking at where the plots intersect, but that can be difficult. So the x naught can just be found looking at the plot and making a rough estimate. So yeah, to understand what root is really doing, it involves a lot of complicated math, Jacobians, multivariable calculus, if any of you have taken that. But the point is, it literally just gives you the answer in 1 second, when this would take an infinite amount of time to solve by hand. So yeah, to find that solution, you would call solve.x at the end to find the solution you want. Yeah? I think, yeah, the way that root works, it assumes that the x naught is a guess to the function, so it knows that that's the variable, because root only solves in, I believe, one dimension. So it knows that you're talking about one parameter only. Yeah, so that's root, and then we can also talk about, Fsolve. So Fsolve is a similar type of function. It basically does the same thing, same complicated math to solve the equation and find the roots of the equation. And yeah, you just use it in a similar sense. You can add extra arguments if there's extra things you want to do to solve, but it's a similar idea, and it's really useful in finding roots of equations that you couldn't otherwise find, basically. Yeah, so here's a little bit more of a detailed explanation. Basically, like I just said, the args part of the function fsolve allows you to pass any arguments to the function that you have defined. So if the function has other, like you were just asking, other arguments besides x, you could pass them here, and it would use that to find the solution. So yeah. Okay, yeah. So now, really quickly, I'm gonna show a demo on curve fitting and root finding.
Yeah, give us just a sec. Oh, we don't want to play fuck teeth. We'll make a new. Give me just a minute. There we go. And we'll go into demos. It's going to be in the data folder. So just, but you're going to be in the numerics folder. All right. There you go. There's a fresh new notebook for you.
Okay, yeah, so to give a quick intro before we dive into what I'll be doing today, James and I both work as part of our research on variable stars. So variable stars are stars that pulsate in brightness over time. They're extremely useful. They can be used as distance indicators to measure the expansion of the universe, and they can just reveal a bunch of cool hydrodynamical things as well and stuff like that. But for today, we'll be looking at the light curve for one of them. So a light curve is essentially the change in brightness over time of one of these variable stars. They are interesting, but they're also sort of difficult to understand. So I'll load in the data really quickly.
Oh yeah.
Yeah, so the data is in the, we'll upload it to B courses, but it's just a CSV file that we can load like this. Called, yeah.
A reminder as he's typing that out. np.load text, we've learned that. Can anybody tell me what the delimiter means? Anybody remember? Perfect. Thank you. And then, yeah. I think I had like an underscore.
Yeah, underscore comma. Yeah. Like that.
I think it was underscore, then X, like underscore X data.
What do you mean?
I got you. Yeah. I think it was the way I formatted this data was weird.
Oh,
there you go.
Okay, yeah. So the X here. So if we just to look at what, I'll obviously make this different, but if we just look at X and Y, it's pretty messy. The key to understand here is also that the way that brightnesses work is the way that magnitudes work is the higher the magnitude, the less bright it is. So we have to define a figure. Yeah, error bar.
So that's in the ultimate plotting guide, by the way. The ax.error bar, like if you checked it out, you could plot like errors that correspond to their y data or x data. You got to do a subplot.
Oh yeah. So yeah. So now we can invert the y-axis. So now you can see here, it's a little big, but that's fine. You can see that the light curve is kind of sinusoidal. In truth, it's not, as we'll discover soon, but yeah, you can see that it's increasing in brightness and it decreases and then it increases again and decreases. And we also have these outlier points and we also have missing phase coverage. So the The x-axis here is phase, so it's essentially the difference from the original period. So at 1, it's completed 1 full cycle. As you can tell, it goes up and down from 0 to 1 and 1 to 2. And yeah, the data is missing obviously because this is real life data taking and there are problems with that. So yeah, so once we have this, we can start to try to fit something to it. So we could try to fit something like, I don't know, some type of combination of sines and cosines maybe. So for example, we could do like 2 pi x plus b times cosine of 2 pi x plus c, where you just have some other constant at the end to add for the offset, because obviously this graph is all around y values of 15 to 16 for the magnitude. So you're not going to have a perfect offset from the get-go. So then, yeah, so for your initial guesses, you could just guess something like 1 to 10 or 16 actually, because that's a better guess. For the A and B, I guess it looks roughly like it could be 1 and 2, so why not? Actually 1 and 1 maybe. And then in order to actually get the parameters like James was talking about just now, you call this curve fit function. You use your f, you use your x, you use your y, you use your par 0, you use your errors, and I'm going to call it with the covariance matrix turned on because it's easier. We don't have to look at the errors right now because as James talked about it, it's kind of complicated. You'll do that in your homework. But yeah, if you run this, oh yeah. Yeah. So if you run this and then you go, that's the best fit first parameter. And then you can get the best fit second parameter. And here's the best fit amplitude. So our guesses were pretty good. So now we could try, if we do this again, pull this over. Yeah. We can plot this again, and then we could try to overplot maybe the best fit function. So we could define some lin space in X because we want to plot over 0 to 2 in the phase. And you could plot so as you can see, the fit is all right, but it's not really great. Yeah, like this is not really actually meant to be fit by a sine and cosine, but you can sort of see the power of these tools. Like you couldn't really have any idea what those parameters would be unless you use curve fit. And as you can see, it's actually a little better than I thought it'd be. It looks pretty good in terms of the amplitudes and stuff. In truth, this is fit by a Fourier function where you have a lot of Fourier terms. If any of you have taken Math 54, Physics 89, Fourier terms allow you to fit any function almost perfectly by summing Fourier terms. I think in the demo that I uploaded, we have the functional form of that. It's just the sum over n, I believe, an cos 2 pi omega n plus bn sine 2 pi omega n. And then, yeah, you just fit a function like this. And I could just open it. Yeah. Let's go here. So here we go. Here's the real fit. So as you can see, it's pretty great. There's missing parts of the data. So it's unclear whether this little peak is physical. So obviously we'd love to have data in these regions, but the point is that this is also using curve fit at the end, I believe. It's just fitting a much more complicated function. So yeah, this is the power of curve fit. It fits the data almost perfectly, besides this little jut here. But yeah, it's pretty great what you can do with a function like this. And this period can tell you, as I was saying, a lot of things about the star and about the universe in general, especially if it's a Cepheid, for example. This star, if anyone was curious, is an RRAB star. It's just a specific type of variable star. But yeah. So, but that's curve fitting. And then, yeah, the next part we were going to go over is root finding. So for root finding, so what we're going to look at here is if you've taken physics 5A or physics 7A, you've probably seen an equation like this where you're matching the energies to the orbit, or no, you're matching acceleration to the expected acceleration of a circular orbit. So in order to solve these equations for the small r's that yield stable orbits, so basically you have satellites that will orbit our moon and our Earth at the same time. So you need to find specific values of r at which you can place them so they'll orbit in a stable fashion according to Keplerian and Newtonian mechanics.
Yeah, I'd just like to add to that. If you show the image,
Yeah.
has anybody heard of JWST, James Webb Space Telescope? It was like a big deal, like literally a couple weeks ago. They just launched a, I think it was like a couple $1 billion telescope that's been in development for 20, 30 years. And they're going to go send it like somewhere in the middle of space. It's L2. Move your mouse to L2. That's a Lagrange point. It's like literally in like empty space, but it's like a stable point in an orbit. So it can just hover there and it can kind of just like stay chilling, and it will stay that way relative to Earth as the Earth moves around the sun. The whole thing rotates with Earth, which is pretty cool. So NASA uses L2 to put like observatories there where they're like on the dark side of the Earth from the sun. So it's like no heat, and it could be an infrared telescope, like only looking at heat of stars millions and millions of light years away, which is pretty cool.
Yeah, so this is a pretty useful application of this root finding. So actually for this one, we'll use another one in SciPy.optimize called bisect, which just defines as the name suggests, I believe it just finds the bisection between the curve and 0. So we'll import that, and then we'll define our function. We can just call it f, or let's just call it L of r, and then we'll have to define a couple variables. So we have g equals 6.67 times 10 to the negative 11th. We have the mass of Earth, which is 5.97 times 10 to the 24. Not that interesting, but the mass of the moon, the radius of the Earth, the angular speed of something in this orbit, and then we return that function where we have, yeah, g times m divided by r squared minus g times little m divided by r minus r squared minus w squared, omega squared, sorry, times r. And then we're going to try to find the roots of this function. So in order to do that, this bisect will take a range that you're looking in. So define some point. The radius shouldn't be probably bigger than the radius of the Earth itself. So we'll just say this is that. And then we'll define an x error where it'll look within this error for points, basically. So then we can say, yeah, this point will be bisect L1 1 comma r minus 1 x total with x error, yeah. And then this function will allow us to, oh yeah. FA and FB.
We tried just using Fsolve.
Yeah.
Might just be easier.
Yeah. I'm just gonna guess something. So yeah. Yeah, so here's a solution. I think it's pretty dependent on your guesses. So this is just one solution to the equation. One of the Lagrange points is 346,000 kilometers away. So I think that's roughly what we would expect. And yeah, we could print it more directly, but essentially this is just a very convenient way to solve an equation like this and get this important result, basically. I'm curious if I change this. No, okay, so yeah, this is the Lagrange point according to Fsolve. Bisect might be actually a little more accurate, which is why we used it. But yeah, this is the power of root finding. I mean, you can see on the picture, here's the different Lagrange points. This, we should have found L1, so this will be 346,000 kilometers away from us, and this satellite can orbit on this in a stable orbit. And yeah, so I guess that's basically it for the demo. Does anyone have any questions? Oh yeah, sorry.
I believe it does, but you might want to try making X not an array. I don't think that'll work, but make it like 5 different values, and I think it might give you.
Okay, yeah.
Make it like a list of values. I think since he only put one X naught value in, it only gave him one answer, but I'm pretty sure it should give you several. Try that. Yeah.
Yeah, there we go. But,
So,
well,
it gave you
well,
one, but it did. I think that's just because they're so similar.
Yeah.
Yeah. So, I guess the takeaway with this, you can inspect it visually, but also you can know that the equation that you're like root finding has 5 solutions just analytically, because if you scroll up to the equation, if you go back, yeah. It should have 5 solutions, but I can't remember why it's not. Something with physics, not important. What is important is that you have a function with however many roots you expect. So say you have like a 5th degree polynomial that should have 5 roots, for example. This will be on your homework, and it'll be written a little bit more clearly so it's not confusing. I believe you'll use Fsolve there. But you give, like, once you know how many roots there are, you give X naught a list, or X naught is a list of guesses for those values. In this case, he didn't know what the X naught, or like what those guesses might be. So since some of his guesses were so close, it's just kind of finding that local minimum in like for that root or whatever. So you kind of have to make educated guesses on that front and compare them to like plotting the equation. You can plot this function as a function of R and see how it, like, where the minima occur, or like where they cross 0 or whatever. So X naught should be a list of how many roots you expect to find of your function. It gets a little complicated with like this function, for example. I think if you scroll down, I think that this one actually has the code that was originally written. Now, the reason why he used bisect in the first place, like why like that, we didn't even talk about that. We just wanted to show you that scipy.optimize has lots of different methods to root find. And in fact, I encourage you to look at some of them if you're like getting 2 different values. Like in theory, Fsolve and root should give you the same thing. But the truth is they have different numerical techniques to solve. And sometimes they give you different answers. So it's good to compare root finders to each other. So maybe if you get an answer with bisect that's different than Fsolve, you should also try root and see which ones give you the most common answers. And more specifically, you should plot it to see, does this even make sense? Because sometimes they fall into like fake solutions, if that makes sense. So you could always go on scipy.optimize. They have like a whole bunch of different functions, and you can like try them all out. But bisect is just one of them. The arguments are a little different, where you could specify like how much of a tolerance do you want it when, or the like function overlaps with like a line or something. But it's not super important. That's something you can Google on your own time. You'll get way more experience with this on the homework. It's like written. It'll be clear. Come to office hours and all that stuff. Does that answer your question?
Yeah, like James was saying, I think the best way to work with this, like to learn this, is to work with it, because it's sort of hard to understand when you're just looking at some problem here with the R's. Yeah, there's some solutions, but the point is that this can solve. For example, I believe in the homework you'll work with a 6th degree polynomial, which will have roots at more reasonable numbers. So you'll be able to look at the axis from say 0 to 100 and pinpoint exactly where the roots might be, and then make those guesses and get the actual solutions. So yeah, I guess then, yeah, if no one has any other questions.
Yeah, we're at time.
Yeah.
Yeah. Any last question? Okay, then in that case, homework 4 due today. Homework 5 will be due next week. And I don't think we have any other announcements other than that. Come to office hours. Have a good one. Is there anything in the chat? Can you check the chat?
Oh,
Third question.
thanks. See you next week.
Go ahead and
How do I stop recording?
just